management. The website OSHA.gov does have a tremendous amount of information available to assist in providing safe workplaces, including access to publications in English and other languages, standards, letters of interpretations, preambles, e-tools, and the on-site consultation services. Maritime and construction industries are addressed in their own right and do not fall under 29 CFR 1910 for general industry. Therefore, gas, welding, and cutting is specifically addressed in both maritime and construction standards. In maritime, there are additional requirements for compressed air and air receivers, and in construction, we include hazardous waste operations and emergency response. In general industry, you will find standards incorporated by reference under 1910.6. And when you visit OSHA.gov, you will find the contact information necessary to obtain a copy of those standards. As you can see, some of the incorporated standards deal with cylinder valve outlet and inlet connections, inspecting compressed gas cylinders, requalifications of ICC 3HT cylinders used in aviation, acetylene, handling of compressed gases, safety relief devices for compressed gases, safety relief devices for compressed gases, storage containers, and air compressed for breathing purposes. With the time we have, today's presentation will highlight aspects of the Compressed Gas Association, or CGA's, pamphlet C6 and P1. Most industrial and commercial facilities will fall under 29 CFR 1910 general industry. Use of compressed gases falls under 1910-101B, where we find ourselves with a short and direct paragraph describing the scope of the standard, which addresses the in-plant handling, storage, and utilization of all compressed gases in cylinders, portable tanks, rail cars, or motor vehicle cargo tanks. Next, we move to the incorporated by reference CGA pamphlet P1. CGA pamphlet P1 published rules primarily to guide users of compressed gases in cylinders based on accident prevention experience. CGA P1 was adopted after numerous accidents occurred during the transportation, handling, use, and storage of these containers. It was found that the accidents could be traced in failing to follow the Interstate Commerce Commission, ICC, requirements to the abuse and mishandling of containers. The goal of P1 is to address gas handling, identification, cap removal, support, pressure regulating devices, and connections. The standard further states in 1910.101B that the in-plant handling, storage, and utilization of all compressed gases in cylinders shall be in accordance with the Compressed Gas Association pamphlet P1. You will see here CGA's definition of a compressed gas from 1965 as incorporated by the standard, and that of the GHS 2012 definition of a compressed gas. These definitions are not in conflict. And here, in the language from a letter of interpretation, I will quote for you. There are more recent versions of the industry consensus standards that are referenced in 1910.101. If the more recent consensus standards address hazards associated with compressed gases that are not addressed in the CGA pamphlets referenced in the standard, 1910.101, 1910.1200, or any other applicable OSHA standard, the more recent consensus standards may provide support for a citation alleging a violation of the OSHA Act General Duty Clause, 29 USC 651A1. If an employer is not in compliance with the requirements of an OSHA standard, but is complying with the requirements of a current consensus standard that clearly provides equal or greater employee protection, the violation of OSHA's requirement will be treated as a de minimis violation. De minimis violations are those having no direct or immediate relationship to safety and health and result in no citation, penalty, or requirement to abate. I will point out the CGA continues to work through a committee system to create technical specifications, safety standards, and training materials to promote and advance safety in the industrial gas industry. And their website, cganet.com, has a wealth of information. OSHA's GHS 2012 classification criteria made for 4 unique classes of gas dependent on what is called the critical temperature. The critical temperature is the temperature of the pure gas where it cannot be liquefied, regardless of the degree of compression. These classes include compressed gas, such as argon, used as a shielding gas in portable welding equipment. We have liquefied gas, such as carbon dioxide, with the liquid dip tube. Next, we have refrigerated liquid gas, such as liquid nitrogen, used for flash freezing food, and dissolved gas, where acetylene is dissolved in acetone and trapped in a porous material. NFPA, also an organization with a committee system, developed NFPA 55, the Compressed Gases and Cryogenic Fluids Code. NFPA defines a strategy for safety training, management and emergency plans, precautions when closing down operations, and building-related controls. An interesting point to know is that the CGA assisted with the initial framework of this standard, which today covers the installation, storage, use, and handling of compressed gases. Today, NFPA continues to evolve and incorporate new practices for improved safety. And even the most recent NFPA edition from 2020 sets forth the following changes. They added a definition for press connect fittings. They changed the code regarding pyrophoric gases and high hazard gas rooms. They added a requirement that pressure relief devices involved with cryogenic fluid piping vents outdoors when the maximum allowable working pressure or maximum process operating pressure is released. They added text to this section on bulk liquefied hydrogen systems regarding setbacks for vent stacks. And they added redirection for liquid nitrous oxide systems to include medical gas applications from another chapter. When you read NFPA 55, you will find the code contains both general requirements and hazard-specific requirements based on the type of gas and the quantity of gas within a defined area, whether it be a control area, indoor area, outdoor area, or use area. Some of the topics specific to these areas will include temperature protections, emergency alarms, pressure relief, and special ventilation components. NFPA has a variety of codes, which addresses gas, among which include NFPA 2, Hydrogen Technologies Code, NFPA 56, the standard for fire and explosion prevention, and NFPA 99, the Healthcare Facilities Code. Today's presentation contains general requirements and apply to medical, corrosive, flammable, oxidizing, pyrophoric, toxic, unstable reactive gases, and cryogenic fluids. Gases are typically stored in cylinders and tanks. As you see from the photo on this slide, cylinders can come in a variety of shapes, colors, and sizes. CGA pamphlet C6 provides the requirement for high and low pressure cylinders. Cylinders can be constructed of a variety of materials, but the key is that the contents have to be compatible with the material construction, the cylinder body capable of withstanding the pressure, cylinder capable of impact resistance to protect during transport, and bear corrosion resistance. Therefore, the containers can be made of a variety of materials, including pressurized steel and aluminum, alloys, and composites. The tall cylinder with a protective ring at the top is a typical cryogenic cylinder. These can come in low, medium, or high pressure configurations depending on the pressure set point of the pressure relief device. These are very specialized cylinders and that you can draw the contents either in the liquid or the gas state. Oftentimes, cryogenic liquid is chosen because of the expansion ratio from liquid to gas. For liquid nitrogen, the expansion ratio from liquid to gas is 1 to 710. For oxygen, which its expansion is even greater at 1 to 875. And ammonia, which is sometimes used in HVAC in the Carnot refrigeration cycle, as energy transfer takes place, expands 30 times. This rapid expansion can lead to condensate formation on non-insulated pipe fittings and pipe runs. For the case of liquid nitrogen, this condensate is mostly water vapor from the air and also contains liquefied atmospheric oxygen. Oxygen enrichment is a fire hazard. Another view of compressed gas cylinders is shown here. To the left, we have a standard cylinder, this one representing a high pressure cylinder with pressures greater than 900 psig and may contain argon, oxygen, hydrogen, and nitrogen. Just to the right, you will see a low pressure cylinder with a dip tube. With this type of cylinder, you can withdraw gas at high pressure or access the liquid phase directly. Common gases include carbon dioxide, chlorine, nitrous oxide, and ammonia. Second from the right, you can see a cylinder of acetylene. This is a specialized container which contains a porous mass in which acetone is used as a solvent to help trap the acetylene into the porous material. This type of cylinder also has fusible plugs which operate as a safety valve if dangerous temperatures are reached in a closed vessel. The fusible plug is a threaded metal cylinder, usually of bronze, brass, or gunmetal, with a tapered hole drilled completely through its length. This hole is then sealed with a metal of low melting point that flows away if the predetermined high temperature is reached. If the initial use of the fusible plug was actually a safety precaution against low water levels in steam engine boilers, but later applications extended its use to other closed vessels, such as air conditioning systems, tanks for transporting corrosives, or liquefied petroleum gases. The cylinder on the far right is a cutaway of the cryogenic cylinder discussed on the previous slide. These cylinders are bulky due to the double wall nature of the vacuum vessel and usually have a tube used to draw the liquid gas back into the headspace to pressurize the container, as well as cool the contents of the container through evaporative cooling. The gas released through the evaporative cooling then is responsible for the venting of cylinders, which can produce high-pitched noises. This diagram represents the important markings you observe on cylinders above the shoulders of the cylinder and below the threaded collar. To transport cylinders on public roadways, containers must have DOT markings in accordance with 49 CFR 178.56. Those will include DOT specification pressures, serial number, manufacturer symbol, test date and tester symbol, permission to overpressurize as marked by a plus sign, a retest date, and hydrostatic retesting extension allowances as marked by a star. The U.S. DOT's Pipeline and Hazardous Material Safety Administration, which conveniently has the acronym PHMSA, provides approval for manufacturers and requalifiers of pressure vessels. Their website, phmsa.dot.gov, has search engines for the approved inspection agencies, cylinder manufacturers, and requalifiers, along with the latest emergency response guide, also known as the ERG, and the National Library of Medicine's WISER software, which are incredibly useful in developing emergency response plans. Contained within the OSHA standards, we have 1910-101A, Inspection of Compressed Gas Cylinders, which states, each employer shall determine that compressed gas cylinders under his control are in a safe condition to the extent that this can be determined by visual inspection. Visual and other inspections shall be conducted as prescribed in the Hazardous Materials Regulation of the Department of Transportation, 49 CFR Parts 171 through 179, and 14 CFR Part 103. Where those regulations are not applicable, visual and other inspections shall be conducted in accordance with CGA Pamphlet C6 and C8, which is incorporated by reference in 1910.6. The lesson here is inspect before you accept. So by now, I hope you've asked yourself, who has to inspect the cylinder? Well, according to CGA P1, the user is responsible for the handling of the cylinder, connecting it, and confirming its contents through labels or other markings on the cylinder before using. It is unsafe to accept and use a cylinder content without having its contents marked. In the picture above, a cylinder refrigerant was delivered with only the shipping declaration of goods describing the contents of the cylinder. I caution folks to have a plan in place to reject unlabeled or mislabeled cylinders. In this instance, the shipper refused to return carriage and left the supposed refrigerant on the loading dock, effectively abandoning the shipment. This took months to resolve. Fortunately, the shipper returned to reclaim their cylinders as they were being charged a demurrage fee. If cylinder content is not identified by marking, return the cylinder to the supplier without using. So let's break this inspection down. Users would check the cylinder as received for obvious damage, determine that all protective caps and plugs are in place, and verify the labels, tags, and shipping papers are appropriate. This also applies to suppliers and distributors filling compressed gas cylinders. I have personally responded to issues involving cylinders that have had gouges, welding marks, and missing pressure relief devices, and relief devices that have malfunctioned, or completely empty or below their fill weight. I've even had gas shipments received with noticeable impurities, including breathing air with oil contaminant. For all of those issues, the key was to reject the shipment. My advice is to have a plan in place to advise end users on what their course of action is to avoid a reactionary response and make it a planned response. In the next few slides, we will show you other issues where the visual inspection of the cylinder requires the cylinder be removed from service in accordance with CGA C6. The photo here shows a cylinder with a bulge. Cylinders are manufactured to a symmetrical shape. When you observe a cylinder with a visible bulge, your cylinder wall has been compromised, either by external temperature extremes, improper use, or even inadvertent overpressurization. Cylinders shall be inspected for evidence of exposure to fire. The picture shows a ruptured cylinder after a fire. Common evidence of exposure to fire are charring or burning on the paint or other protective coating. I have observed cylinders repainted after high heat exposure near a furnace, which is not a good indicator that the fire extinguisher will perform. Burning or sintering of the metal. Sintering will appear like the surface of a sponge. Distortion of the cylinder. Function safety devices, and melted valve parts. General corrosion resulting in pitting reduces overall cylinder strength. CGA C6 also explains that to fix corrosion limits for all types of cylinder designs and sizes of cylinders and include them in the pamphlet is not practical based on the cylinder designs and the materials of construction. With that said, CGA 6 did give us 4 rules, which are cause for cylinder rejection. 1, below tear weight. 2, extent of isolated pitting. 3, line of corrosion. And the 4th, cylinder wall below the minimum allowable thickness. Specifications are available in CGA C6. For portable cylinders, the solution by now probably seems easy. If in doubt, get it out. However, larger or fixed cylinders will require additional expert investigation and planning to mitigate the hazard from pitting. Oh, this slide does give me a moment of pause. Let's take a moment to look at the photo of the cryogenic cylinder that ruptured as a result of a plugged relief valve. Well, I spent years training people not to tamper with safety relief valve devices or attempt their own repairs on valves, regulators, or safety relief devices. I observed many occasions where employees and management alike cobbled together regulators and made quick repairs to safety relief devices, despite the risk of harm to themselves or others. It is important that work rules are in place to prevent tampering, altering, or repair of cylinders, valves, and safety relief devices. An effective rule must be communicated and then an extensive follow-up with employees and management. This follow-up hopefully includes going to the user areas and asking pointed questions about their work activities. And if any manipulation has been done on the storage and delivery devices for the compressed gas, if so, what was done? When was it done and who did the work? You should also have an effective disciplinary program in place. Okay, on the lighter side, or maybe not. Cylinders must not be used as rollers or supports or for any other purposes than containing gas. I wish I could tell you that I have not seen this before, but once I was in a fabrication shop and they had empty shielding gas cylinders on their side, moving a large piece of steel into place. They said they were using the cylinders because the new guy took out the trash and burned the trash along with the wood poles they would normally use to move the metal. CGA P1 stipulates that the cylinder valve remain closed at all times, except when in use. This is the most secure means to prevent gas from leaving the cylinder. Manufacturers often suggest fully opening or closing cylinder valves slowly and using this regulator to adjust delivery pressure. Well, early in my career, I worked in the laboratory with a scientist who had been trained to use the cylinder valve as a regulator. As the tank pressure diminished, he asked that I initiate gas flow to the hood. He had already fully opened the regulator and had previously used the cylinder valve for flow control. Therefore, when I went to slowly and fully open the cylinder valve, a rapid overpressurization of the transfer line occurred and ruptured, which resulted in a partial loss of hearing for months. Not one of my best working experiences, to say the least. P1 further explains that the user must notify the cylinder owner if any foreign substance might have entered the cylinder or the valve. It is customary to provide the cylinder's serial number to the cylinder owner at the time of the report. Remember, the cylinder's serial number is stamped on the neck of the cylinder. Cross-contamination is foreseeable when you have a cylinder connected to another cylinder or process and a pressure drop occurs across the connection where a check valve is not installed. When the cylinders are used in conjunction with electric welding, precautions must be taken against accidental grounding compressed gas cylinders and allowing them to be burned by electric welding arc. To prevent cylinders from becoming part of the electric circuit, there should be insulating material in place. In order to prevent cylinder damage from arc burns, users must be trained not to use the cylinder for grounding, strike an arc on the cylinder, not to fasten the cylinder to the work table or touch the grounding connection to the cylinder. As a compliance officer, I have observed employees purposefully strike an arc on a cylinder, as well as hang the torch over the regulator, which in turn arced on the cylinder. The best practice is to have a hanger specifically for the welding leads. Here's an example of cylinder damage from a deposit of weld metal, which warrants removing the cylinder from service. In CGA C6, cylinders of arc or torch burn shall be removed from service. Defects of these nature can be recognized by the removal of the metal or scarping or cratering, sintering or burning of the base metal, and heat-hardened affected zones. In CGA C6, cuts or gouges or digs reduce the wall thickness of the cylinder and are considered to be stress raisers, and the cylinder should be removed from service. As a compliance officer, I have observed both cuts and gouges on cylinders, mainly in manufacturing facilities. The cuts often occurred where handheld grinders were conveniently hung over regulators. The gouges were more often observed where the cylinders were removed and dropped onto hard surfaces over time. Once a cylinder is moved, it should be guided into place and not permitted to strike against other surfaces or cylinders violently. At another point in my career, I watched a worker return to our shared workspace with a full cylinder. As they tipped their cylinder cart vertically, they unstrapped the cylinder and then removed the cap. And in order to visualize the threaded end, the valve stem, they simply guided the cylinder back towards the workbench without the cap. When almost in position, the worker reached back to move some hoses and pick up the regulator attached to the said hoses. The worker lost handle of the cylinder and its base slid along the tiled floor. The valve stem struck the edge of the workbench and the cylinder was propelled by the rapid release of gas from the broken valve stem. The cylinder broke through two cylinder block walls before coming to rest. Thankfully, no one was injured, and thankfully, the cylinder contained only nitrogen. While I am grateful no one was injured, this was one of those lessons you never forget because the outcome could have been much worse. You will notice cylinder caps have at least one opening, but those are not designed as lifting points. They are intended to allow for valve inspection and prevent gas from being trapped inside the cap if there's a leak at the valve stem or if the pressure relief device is activated. The photos of these modified caps were taken during an enforcement inspection. Even though the welds in the ring may appear sturdy, the threaded collar receiving the cap is only tack welded onto the cylinder body. Moving by the ring on these caps is a fatal design flaw and not an appropriate lifting device. Cylinders must also not be lifted by a magnet. Just imagine if there's a loss of power and the magnet cuts out, losing the load. The resulting crush by hazard will be devastating. Slings, ropes, or chains should not be used unless provisions have been made by the cylinder for appropriate lifting attachments, such as lugs. A crane may be used when a safe cradle or platform is provided to hold the cylinders. Any attachment points on the cylinder also must be approved by the cylinder manufacturer. It is best to avoid dragging or sliding cylinders because it is safer to move cylinders by using a suitable hand truck, forklift, rolling platform, or similar device intended for the secure transport and unloading of a cylinder. In a nutshell, the cylinder must be firmly secured for transporting and unloading. In this photo, there is no protective cap for the valve stem, nor is there a means to prevent the cylinder from rolling off the forks of the forklift during transport. DGA pamphlet P1 also addresses the storage of cylinders. Where gases of different types are stored at the same location, cylinders should be grouped by types of gas, and those groups arranged to take into account the gases contained. The separation also should account for storing charged cylinders versus the empty cylinders, and the layout arranged so old stock can be removed first with minimal handling of other cylinders. The storage area should also be prominently posted with the names of the gases stored. Imagine how a first responder or a fire department's response could change if they could observe the names from a distance, because the gases inside the storage area had their names prominently posted. Cylinders should also be protected against tampering by unauthorized individuals. Usually this will involve a cage and a lock. And if you're lucky enough to have gas storage rooms, they should be dry, cool, well ventilated, and where practical, fire resistant. The key here is to keep the storage temperature below 125 degrees Fahrenheit, above freezing, and the cylinders away from sources of heat. Well, this may lead one to consider storage below grade, but those two should be avoided because gases that are heavier than air can displace oxygen, creating an asphyxiation hazard. This may seem self-evident, much like a welder not taking their tanks into a trench, and I have observed a number of occasions where gas cylinders were conveniently tucked into underground utility tunnels and basements with their users' insistence that there was no hazard. However, with clear workplace policies and training on cylinder storage, you can avoid the unnecessary confrontation during follow-up inspections of the cylinders. On the left of this photo, you see a cryogenic cylinder filled with liquid nitrogen, and to the right, over a dozen full cylinders containing a variety of gases. This is an outdoor storage area off an elevated loading dock. In this photo, I am standing about 30 feet away from the stored cylinders, and there's no prominent posting with the names of the gases stored. The reason the employer gave for not prominently marking the cylinders? Security. The employer asserted that the prominent markings would jeopardize the security of the cylinders, even though they were in locked cages. Finally, when we take another look, we can see in the background a grate with multiple horizontal lines, or fins. This is an air intake. Prominent postings were not their only issue here. With regards to the storage of flammable gases, as stated earlier, indoor storage should protect the cylinder, be well ventilated and dry. Due to the greater risk of fire and explosion hazards, cylinders should be stored a minimum of 20 feet from flammable or combustible materials, including other oxygen cylinders, unless there is a suitable fire barrier in place. This includes reserve stocks of cylinders. Reserved flammable gases should not be stored with cylinders containing oxygen. NFPA 55 also provides safe separation distances. For most classification of gases, a 20-foot separation is required, unless it is an inert gas as represented here by the green-colored cylinder icon. Distances can be separated by a fire-resistant barrier with half-hour rating. The key is that the fire-resistant barrier has to interrupt the line of sight between the cylinders. I want to remind everyone, cylinder color is not an indicator of content, but in this case, it made for a really nice graphic. The photo on the upper right shows an oxygen cylinder stored within 20 feet of highly flammable refrigerant. A 20-foot separation of fire-resistant barrier is required here. Meanwhile, the photo on the lower left is a grouping of empty nitrogen cylinders. These empty cylinders previously filled with inert gas require no additional separation. Here's an example of what I would find in an establishment. I walk into a shop. First, I scan the ceiling for objects overhead, and then the floor for slip, trip, and fall hazards. Then I look for the marked exit routes, and here's when I observe compressed gases at the exit and in the exit route. Upon closer inspection, I found unsecured oxygen and acetylene cylinders stored together. Also remember, cylinders stored indoors must not be located near exits, stairways, or in other areas normally used for the safe exit of people. These issues were corrected by the employer, but as you can probably see from the dust and cobwebs, they had been there for a while. Do not store cylinders near highly flammable substances such as oil, gasoline, or waste. At this establishment, oxygen and acetylene were stored together with flammable diesel in a 55-gallon drum of waste. This was not their only issue, though. The acetylene and oxygen stored strapped together did not provide 20 feet of separation. Here you see on the left a powered industrial vehicle with its propane cylinder not secured. While the OSHA standard on powered industrial vehicles requires any power-operated industrial truck not in safe operating condition be removed from service until repairs are made, the mere use of compressed gas requires the cylinder be secured prior to use. The same can be said for the photo on the right, where the tall red cylinder of flammable argon hydrogen is unsecured and within 20 feet of a cascade system of 8 oxygen cylinders. The propane was left unsecured because the employee didn't have the right tools to adjust the straps with a new tank. So he connected the tank and drove to get the needed tools to secure the straps. As for the argon, hydrogen, and oxygen system, this was the employer's attempt to meet a customer deadline and was described as a temporary installation as they were waiting for the concrete pad to cure for the bulk tank installation outdoors. The bulk nitrogen tank had already been installed and being used inside the fabrication shop. However, there is no provision for temporary installations and certainly no provision for having the argon hydrogen unsecured. Cylinders can be plumbed, though, from protected locations to enable job site use. In this situation, the argon hydrogen cylinder was stored in close proximity to the plasma cutting table, and you can see the hot berries rolling on the table surface and the flammable cardboard nearby. This was a creative resolution to propane storage at an establishment. To keep cylinders protected and away from locations where they may be struck by heavy items, they converted a truck dock to a propane racking system. The empty cylinders are placed on the top rack and full cylinders on the bottom rack. Compressed gases need to be protected not only for cuts and abrasions, but heavy objects that can strike or fall upon them as well. For outdoor storage, please remember the cylinder temperatures must not exceed 125 degrees Fahrenheit, so storage in direct sunlight may not be realistic in some localities. If the desert animals don't want to bother with daylight, chances are your cylinders will not either. Also, a suitable foundation from the ground should be provided to prevent rusting and pitting of the cylinder base. The shading, as you see in this photo, can be an effective method to reducing cylinder temperatures below 125 degrees Fahrenheit. CGAP1 also addresses the thawing of cylinders when cold or when there is snow and ice accumulated on the cylinder. Users can thaw at room temperature or have the option to warm the cylinder with water that does not exceed 125 degrees Fahrenheit. Under no circumstances should a flame be permitted to come in contact with a compressed gas cylinder. That will cause a rapid expansion of gas in the localized area of the heat source and lead to structural damage of the cylinder. This may result in a hazardous explosion. Weather protection structures for outdoor storage areas are addressed in NFPA 55 without being classified as an indoor storage or use space. However, explosive materials and materials presenting a detonation hazard must have explosion control requirements met, which include, among other items, barricade construction, explosion venting, or explosion prevention systems. NFPA 55 has addressed storage area temperatures like CGAP1 did earlier. NFPA expands on the requirement and includes material-specific provisions for the construction of outdoor storage. Finally, NFPA also addresses where storage or use areas can be placed. Specifically, NFPA 55 specifies storage and use area distance from lot lines, public streets, and public ways. When evaluating a site or analyzing an installed system, you will need to determine the type of compressed gas, quantity and pressure of gas stored and used, piping diameters, as well as site characterization to chart out the minimum distances between the public spaces and the gas. NFPA defines building control areas. At first, it may seem trivial, but it is worth a recap. The control area is that part of the building where hazardous materials are allowed to be stored, dispensed, used, or handled in quantities not exceeding the maximum allowable quantity. The indoor area is the area within the building or structure, including the weather protection structures. And the outdoor area is just that. And finally, the use area is the location where the material placed into use is situated, whether it be indoors or outdoors. When we talk about fire-resistant construction, you will want to check with your local code official and the authority having jurisdiction for your area and the codes they have adopted. The diagram on the lower left is intended to show you an example of a fire-resistant construction for a 30-minute wall from the fire side, which could be either side to give a 1-hour rating. The materials of construction will need to be in accordance with ASTM E119, whose rating details are used to calculate fire rating of the assembly. On to another point to consider. Nesting is the practice of positioning a cylinder so that at all times it has 3 points of contact. It is important to understand that the term nesting, as that will be the term used to describe how cylinders will be secured at the gas supplier's facility and distribution warehouses. Nesting is not permitted at user work sites, but is considered an equivalent means to secure the cylinder from falling. On the left side, you see the top figure where 7 cylinders are placed against the wall. This is nested wall support, and each of the cylinders has 3 points of contact. On the bottom figure, you will find each of the 10 cylinders again has 3 points of contact, despite a wall not being present. This is nested unsupported. Now take a look at the photo on the right. Do you see the yellow cylinders in the middle of this photo and the green cylinders in the lower left corner? Now carefully observe the corner yellow and green cylinders. They only have 2 points of contact. Those 2 cylinders are not properly nested. Just to refresh everyone here, for users of gas, not the manufacturers and distributors, we will need to be certain cylinders are properly supported and secured to prevent them from being knocked over. Moving on to gas delivery from the cylinder. Pressure regulating devices must be used and set to a pressure lower than the lowest rated component in the system. For example, if I have a cylinder at 2200 psi delivering gas into a pressurized vessel at 500 psi and choose a transfer line rated for only 300 psi, I have what is called a bad day when the 300 psi line ruptures. Now, let me take a moment for you to consider system pressures. Remember that line that became overpressurized and blew up right next to my head, resulting in temporary hearing loss? I will never forget, nor will the next person that this happens to. There must be work rules in place to ensure compressed gases are paired with proper regulators. Users must also be trained not to alter the regulator or its fittings, or force connections to fit properly. At one accident investigation, it was determined that the pressure relief disc of a reactor ruptured as a result of a rapid rise in temperature inside a chemical reactor. The hydrogen gas was under continuous flow into the reactor, and when the contents reached their flash point, a hydrogen fuel flame was jetting out of the rupture disc opening. The hydrogen burned cleanly and no flame was visible, but the heat was obvious. Workers were able to use a fire extinguisher aimed at the reactor and reach the cylinder valve to stop the flow of hydrogen. Thankfully, no one was injured. Shortly after, a good deal of discussion was had by all on a variety of methods to prevent this from recurring, including how to vent relief valves and the installation of flow control devices on flammable gas supply lines. Here you have an example of a check valve installed on the line side of a regulator in the upper right photo, and below center is the result of a flashback to the cylinder, resulting in a catastrophic failure of the cylinder. If you ever suspect gas cylinder, tank, or manifold is about to become contaminated by the process, look to protect the compressed gas container by installing a suitable trap or check valve. This will avoid serious accidents caused by flashbacks, reverse gas flow, or other contaminants. Installation and use of proper regulators, piping, and its related equipment also applies to cylinder manifolds. For example, chlorine and hydrogen gas will not be friendly to copper piping. You will want to check the manufacturer specifications on chemical compatibilities for tubing, piping, and regulators. Regulators are equipped with CGA numerical designations to identify type of gas and working pressure of the regulator. Unless you have written permission from the supplier that it can be done safely, do not intermingle regulators, gauges, hoses, and other appliances designated by CGA numerical designation with pressurized gases under different CGA designations. Gas suppliers are good at providing CGA selection charts for the gases they supply. Adapters that can change a container CGA connection from one product to another shall not be permitted by users. However, there are adapters used in medical service, which do have additional requirements. This was an interesting inspection. I observed a jeweler's torch. You will note it is a small welding torch. Flexible rubber hoses were used to transfer the fuel and oxygen from the cylinders. The oxygen supply hose was becoming brittle, as maybe you could tell by the discoloration. Also, copper wire was used to hold the tubing onto the taper fitting of the regulator. CGA P1 states connections to piping, regulators, and other appliances should always be kept tight to prevent leakage, and where hose is used, it should be kept in good condition. To withdraw content, CGA P1 explains we need to point the cylinder valve opening away, open the valve slowly, and never use wrenches or tools unless specifically provided or approved by the manufacturer. One example of a specialty tool is the acetylene cylinder valve key. Work rules should be in place to communicate with users to avoid the use of wrenches on valves equipped with hand wheels, and instead direct them to contact the supplier for instructions. Chances are the valves that are hard to open are frozen due to corrosion, or even a previous user's failed attempt to stop a leak. Oh, don't sugarcoat those rules. This would be like telling your 2-year-old, no, they have to take a nap. For example, never hammer the valve wheel in attempting to open or close a cylinder valve. So once finished with the compressed gas, you will need to remove the regulator. First off, release the line pressure if you have a single state regulator. This step involves closing the cylinder valve and then reducing the line pressure to 0. If you have a manifold with a continuous flow of gas into a system, you may need to perform a single or double block and bleed using the block and bleed valves. In a double block and bleed situation, you will close the block valves and open the bleed valve between to release the line pressure so you can safely disconnect the cylinder. When connecting gas cylinders or troubleshooting pressure loss, never use a flame to detect flammable gas leaks. It is much safer to use soapy water, gas detector, or better yet, if you have the funds, an ultrasonic leak detector. If you have not had the opportunity to use an ultrasonic leak detector, you are missing out. On a practical note, you can also detect hairline fractures along a pressurized system with relative ease and less soapy mess. Before we end today's presentation and our discussion on personal protective equipment, also known as PPE, I want to take everyone back to the basics with the hierarchy of controls. For those unfamiliar with this hierarchy, I implore you to take note, as this is a fundamental concept of safety and health management. As professionals, we seek to control hazardous exposures causing health and safety issues. The graphical representation places the greatest and most effective protection at the top of the pyramid and lesser effective methods of protection at the bottom of the pyramid. Remember, prevention is better than protecting, but reacting is usually why an adverse situation progresses. If you cannot prevent the hazardous exposure through elimination or substitution, the next step is to implement engineering and then administrative controls and work practices. If you still cannot prevent the hazardous exposure, you must rely on personal protective equipment if the operation will continue. However, PPE is really the least effective option, and unfortunately, I've seen too often where it was an employee's only option. When it comes to compressed gases and PPE, employers are required to start off by conducting a workplace hazard assessment. This assessment must have a written certification that identifies the workplace evaluated. The person certifying the evaluation has been performed, the dates of the hazard assessment, and which identifies the document as a certification of hazard assessment. Much like a job hazard analysis, often referred to as a JHA, the tasks involving a hazardous activity will be evaluated and appropriate PPE provided to the employee, typically at no cost. This PPE may range from safety glasses and steel-toe shoes up to chemical protective suits and self-contained breathing apparatuses. It is also imperative that PPE fit the user. On the upper right-hand corner, you can see 3 types of gloves. The blue glove on the left is a glove typically used for cryogenic liquid. The lighter blue glove in the middle is a nitrile glove, and the glove on the right is a terry cloth glove used for heated items. This is a very short demonstration on what could happen if liquid nitrogen got into each one of these gloves. Typically, cryogenic users wear long sleeves or gauntlets covering the glove openings. This keeps the liquid from entering through the top of the gloves. But the question at hand was, how different would each of these gloves behave if liquid nitrogen were inside them? What we observed was that the liquid nitrogen poured through the openings on the terry cloth glove and vaporized quickly in the nitrile glove. However, with the cryogenic specific glove, it retained the liquid nitrogen the longest. Well, this made a great deal of sense. Not only does the cryogenic glove have a tighter fabric weave, but it also has a layer of waterproofing material to keep moisture out, and in this case, the liquid in. The take-home message here is that the PPE has got to fit. And in the case of cryogenic gloves, you want to be able to throw your hands down vigorously to remove the gloves in one quick movement. Otherwise, the cryogenic liquid will remain in contact with your skin longer. One last note on PPE pertains to respirators. If your establishment handles and uses poisonous gases, appropriate masks or self-contained breathing apparatus must be available for immediate use. This equipment should be located convenient to the workplace, but kept out of the area most likely to be contaminated. And the last point I wanted to share with you involves injection hazards of compressed gas. Often we see employees cleaning equipment and themselves off with compressed air. OSHA requires compressed air used for cleaning purposes to be reduced to less than 30 psi and have effective chip guarding and PPE in use. I want to thank you for inviting Carlos and I to share this presentation on compressed gases, and I hope it has been informative. And at this time, Carlos and I would like to take any questions you may have.
And Joneen, I would like, and Carlos, I'd appreciate it. Seems like we were still having some problems in the beginning, so if you could pop up the disclaimer again and go through that, make sure everybody gets it.
We got to do one at a time, huh?
I guess so. I thought I'd be able to slide. Wonder if I did up here. Huh. Nope.
Yeah, I found out YouTube was still lying to me. It was streaming on my end, but YouTube hadn't actually released it for some reason. I'll have to investigate that.
Oh, well, I certainly hope everybody got a chance to enjoy the whole presentation. Joneen did an excellent job. And, you know, our disclaimer is pretty much always the same on any kind of material you might see from the U.S. Department of Labor. I'll go ahead and read through it just so it's on the recording. This U.S. Department of Labor OSHA presentation is for instructional, educational, non-commercial purposes only. Some material may be subject to copyright and trademark protection. Copyright and distribution of such material is not authorized without permission, and that would be from us. So if you would like any of this material or to use any of it, you can contact Joneen or myself. At this time, we could take some questions, Steve.
Yeah, thanks, guys. Anybody have any questions? Please type them into the chat box now. We're certainly getting some thank yous and you know, appreciative of the refresher and interesting presentation, those sorts of comments. How about some questions, guys? Still no questions.
I guess you came across as being incredibly shy, Joneen. We don't bite, we promise. And we don't know where you're asking questions from. Total amnesty here.
I think you just did such a great job of it. Everybody is full of information now.
Well, and it can always be watched again later too, so hopefully that'll help some.
Absolutely. Yeah, definitely some good comments from the field though. So, all right, guys, give me just a couple more seconds and see if you have any questions.
Yeah, Steve, if you could forward on the comments, Joneen and I would appreciate seeing those.
Sure. They're actually, if you just, once the replay's up, the easiest thing is probably just skip through. They reappear live in timing with the actual stream. So, wow. Okay, we do have a question. Let's see, let it pop up here. Just a second. Okay, looks like we actually have a couple. Good. All right. So first question is, what is the applicability of piping codes? And that comes from Roger.
I think I probably need a little bit more specificity on that one. For piping codes, we will follow industry consensus standards.
Yeah, it's going to be mostly like for welding gases and things, it would be AWS codes. But yeah, those are incorporated by reference. I think we have a slide on that.
Okay, and Roger, if there's anything else, go ahead and fill in some more details and we'll get it covered. Richard asks, are there any requirements for leak detection, especially for cryochemicals?
That will be dependent on industry, and most common reference would be the NFPA 55 or the industry-specific standards that NFPA has addressed, as well as any kind of local codes or the authority or having jurisdiction.
Yeah, one of the few OSHA requirements I'm aware of would be for hydrogen gas around high voltage electrical generation. That's a specific one I'm aware of, but I don't know of a whole mess of other ones.
Okay, I will share just a couple of these as they're coming in. Also give somebody some time to ask some more questions if they want. But this one I just thought was really cute from Christina. Love the slides showing bad examples.
I would rather go ahead and learn from somebody else's example than my own. So thank you.
Hear, hear. Yes, indeed. And this one is good. I think this one really kind of sums it up from Tom. He says, I plan to watch again. Very informative, fast moving. And of course he says, I had a question early on but forgot it momentarily. So Tom, if you think of it again, go ahead and bring it up. So I suggested writing it down. All right, let's see. I guess Roger's trying to clarify. He's asking about ASME piping codes.
If you go to 1910.6, ASME standards are listed in the incorporated by reference for general industry.
Yeah, and just some background on incorporated by reference. Whenever you have a standard that has some kind of language in it that you find is sounds subjective, like acceptable, approved, safe. Some of those terms would come from an incorporation by reference of a standard like an ASME standard or an ANSI standard. As part of that requirement, as part of that OSHA paragraph or section, you'll find that, like Joneen is saying, you go back to 1910.6 and you find all the things that are incorporated by reference. And if the subject of what the standard is discussing is one of these, is also the subject of one of these standards incorporated by reference, then those words mean a lot. So that's the applicability, I guess. In my mind, that would answer your question, Roger, I hope. That, the standards incorporated by reference are what we're referring to when we use terms like that within those, applicable or, reference standards that we have. So we may not publish the entire standard, but we incorporate it by reference so that we can make standards and discuss what is acceptable and what is common or what is accepted by industry.
Okay, thanks. And this is one I'll go ahead and read it, but I think I know the answer. You guys aren't in a position to talk about this, but Richard says, recent N2 releases in industry causing injuries. So is that correct? You guys aren't really in a position to talk about that right now?
If there's an open investigation that OSHA is currently conducting regarding what this gentleman's talking about, and I believe there is, then no, we're not at liberty to discuss that.
Okay, thanks. Yeah, I was pretty sure that was the case, just didn't want to answer on your behalf. Yeah, this was another good one from John. Great presentation. It says, this often happens, a few, quote, they did what, unquote, moments.
Yeah, OSHA always has a lot of pictures of bad situations. So there's a lot of them on our website. We have a nice picture gallery on our OSHA website, and there's a bunch of what we call our e-tools, which are electronic tools. They're learning tools, and they're short workshops that you'd go through to see some of those hazards, and where they're discussed at length, and we talk about how to abate such conditions, meaning correct such conditions, or talk about all the compliance matters related to those hazardous photos you see.
Okay. All right. Well, great. That seems to be it. So. Thank you both very much for a very informative and I would say timely topic for us, at least here in Georgia. And let's see, somebody did come back in. Yeah, Richard's saying he is asking about that, but he also did a cryo project and wondered about how to detect an N2 release. So I think that's just a general, how would you detect that?
Probably one of the most common methods of detecting nitrogen release is using oxygen sensors. And they'd be oxygen sensors placed in the area of use, or the use area, as NFPA 55 defines, to detect indoor quantity or any kind of displacement of oxygen inside the space because of the asphyxiation hazard that the liquid nitrogen can represent.
Yeah, it's going to displace oxygen, so naturally, any kind of a space that you're looking to detect in, you'd be looking for a drop in oxygen content and an increase in nitrogen content. And most 3 gas meters will be able to do that for you.
Okay, great. One last shot here. Yeah. Okay, that appears to be it. So. Yeah, so again, thank you both very much. Remind everybody to go ahead and subscribe to the YouTube channel and click that notification icon so you get told when new things are coming up. In addition to these PDHs every month, we're also trying to add in some other events like our E-Week award ceremony that happened a week or so ago. And the ticker's showing you where to send your emails for your PDH certificates. And if you're not already a GSPE member, we encourage you to look into joining and becoming active. Don't just join and pay your dues, but also become active. Go to gspe.org to find out lots more details about what we have going on. So, and with that, once again, thank you both, Carlos and Joneen. I hope you guys have a wonderful evening.
Thank you, you as well.
Thanks.
Thanks for having us.